Above sea level and below is a world we need to care for. And being a marine professional, you play an important role in helping to protect this vital natural resource. We're facing major challenges, from climate change to the breakdown of our marine ecosystems. The Institute of Marine Engineering, Science and Technology, the IMarEST, is the global home for marine professionals. We're the first institute to bring together marine engineers, scientists and technologists, creating an international family. Worldwide, we have 22,000 members in over 120 countries with over 50 branches. We offer a level of membership to support you at every stage of your career, from students and graduates through to members and fellows. We set global standards by offering professional qualifications and certifications up to the level of chartership. We also accredit universities and college courses all over the world to endorse the high-level skills of their graduates. So whether you're an engineer working on an offshore wind farm, ship crew on a cargo ship, or a marine scientist surveying coral reefs, IMarEST membership helps to advance your career. We are dedicated to sharing knowledge through world-leading resources for the maritime community. You can join one of our technical special interest groups and drive progress in the latest technological and legislative fields. And we give you a voice on the global stage. We hold official statuses at several intergovernmental organisations and attend United Nations level meetings to help develop regulations and policies. This means you can share your expertise and have a real impact on the future of the marine world. This influence is important. A report by the Intergovernmental Panel on Climate Change on the State of the Ocean showed climate change is causing the ice to melt, water levels and temperatures to rise, and species to move habitat and perish due to human activities. Our industry needs to lead the way in lessening these effects. We need to continue developing net zero carbon technologies and reducing our dependence on fossil fuels. The marine industry clearly has its work cut out. There are many challenges facing the oceans, such as overfishing. Our members need to develop ideas to ensure food security. Already, drones and autonomous surveillance are helping to control illegal fishing activity. We also have to grapple with the biggest technological revolution in history, with artificial intelligence transforming shipping and the entire marine infrastructure. This not only brings us new challenges, but will also allow us to explore new frontiers such as the ocean deep. The global marine economy is estimated to be worth $3.5 trillion, with an estimated 80% of all life on Earth found under the ocean surface. Our vision is a world where marine resources and activities are sustained, managed and developed for the benefit of the planet.
Good evening, ladies and gentlemen. My name's Andrew Tyler. I'm President of the Institute of Marine Engineering, Science and Technology, and it's my pleasure this evening to be the Chairman of the IMarEST Lord Kelvin Lecture. So a very warm welcome to all of you here this evening, but also somewhere in the order of 140 of you who are live streaming this evening's lecture. Everybody is very, very welcome. The Lord Kelvin lecture series was established in memory of Lord Kelvin's presidency of the Institute back in 1892-3. And although he was very, very well recognised as a pure scientist, he was equally successful in the application of science and engineering. And for us in the maritime community, his patent of the ship's compass and the sea sounding apparatus are two inventions which are now absolutely commonplace in our industry. The Lord Kelvin lectures are given by distinguished members of the maritime community who are taking Lord Kelvin's foresight and applying it to the development of future technologies. Tonight it's a great pleasure for us to have Professor Phil Weaver with us. Phil trained as a geologist. I first met Phil about 20 years ago when I was on NERC's Science and Innovation Strategy Board, and since that time he became the Director of NERC's Strategic Research Division at the National Oceanographic Centre in Southampton in 2006. He left NOC in 2010 to set up Seascape Consultants Limited, which coordinated the EU-funded MIDAS project looking at the environmental impacts of deep-sea mining. Phil's now a partner in 2 EEC-funded projects, Blue Nodules and Blue Harvesting, that's developing a deep-sea harvesting system for manganese nodules with a reduced environmental footprint. And he also coordinates a project to assist the International Seabed Authority in developing regional environmental management plans for polymetallic sulfides in the North Atlantic Ocean. It was about 30 years ago, I vaguely remember writing an undergraduate essay on manganese nodule mining. 30 years on, I've got a hunch that deep sea mining may have come of age. So it's a great pleasure to hand over to Phil to enlighten us.
Thank you. I would like to thank IMarEST for inviting me to give the Lord Kelvin lecture. I'm afraid I'm not an engineer in the mould of Lord Kelvin, not an engineer at all. I was, as said, originally a geologist, so I won't be able to answer your detailed engineering questions, but I'm sure many of you in the room will be able to. So I'm going to structure my talk along the line of the 3 mineral types that are found in the ocean. So the first one, manganese nodules. These are located very deep in the ocean, between 4,000 and 6,000 meters water depth. They have a whole range of metals in them, but the ones that are more likely to be extracted if they're harvested are nickel, cobalt, copper, manganese and molybdenum. They just form a very two-dimensional layer, just potato-sized pieces of rock just lying strewn across the seafloor. And because of that, the areas that would need to be mined would be very large, perhaps in the order of 60 square kilometers per million tons of ore. And a single mine would probably extract about 2 million tons of ore at least per year. The second type of resources is formed in a very similar way by precipitation from the ocean, and this time onto hard rock. So where hard rock outcrops, you can get these crusts of polymetallic deposits. And these occur, again, in a wide range of water depths, but the most economic ones are between about 800 and 2,500 meters water depth. Similar set of metals, copper, nickel, cobalt, molybdenum, but also possibly platinum and technetium. There's a possibility of rare earths, but it may not be that's the best place to get them from. These again are a two-dimensional deposit forming crusts 10, 20, 30 centimeters thick on hard rock. And again, that requires a large mine size of maybe 13, 15 to 40 square kilometers per million tons of ore. The third ore type are massive sulfides, and these are completely different to the other two. And these are known on land as with analogous type deposits. These are found in a wide range of water depths, down to 5,000 meters, but the metals here are quite different. So there is copper again, with zinc, and particularly gold and silver. These are, as I said, a three-dimensional deposit, so the mine size here is going to be quite small, very similar to a mine you see on land, maybe less than 1 square kilometre. Where do they occur in the world? Well, this map shows pretty much all of them. You can see these lines with orange dots going down the middles of the oceans. That's where the polymetallic sulfides are formed. On ocean spreading centres where the plates move apart. The nodules are found in the deeper parts of the ocean where you don't get much sedimentation and they don't get buried very quickly, so particularly the Central Pacific, and that's the area which most of the licensing for manganese nodules is concentrated on. And the third deposit are cobalt crusts, shown here in yellow, and these occur usually on oceanic islands, and the older the island, the more time, or not islands, seamounts, oceanic seamounts, and the longer the seamount has been in existence, the longer it's had time to accumulate a thick layer of this crust. So these occur particularly in the Pacific and the Western Pacific. Those are the sulfide deposits where licenses are already approved. So I'm only going to talk about what's known as the area with a capital A, which is comes under the jurisdiction of the International Seabed Authority and represents all the seabed which is not under the control of individual states, so not continental shelves or extended continental shelves, but the rest of the ocean. And the International Seabed Authority, not license, but they award contracts to individual companies to look for minerals and then ultimately to mine those minerals. So you can see here that mining for nodules contracts for mining for nodules have been going for quite a number of years now, and more recently we've had contracts awarded for exploration for sulfides and now for exploration for cobalt crusts as well. So I'm going to take you through some aspects of mining for manganese nodules, looking at the environmental aspects and some of the engineering progress to date. And that was what they looked like on the seabed. Here you can see all the bright colours in the centre with the irregular squares. These are all licensed contract claims of individual companies or states, and each one can be a maximum of 75,000 square kilometres, within which they're meant to explore over a 15-year period and then come up with a plan to go mining some parts within that area. Around the outside, the 9 large areas are areas of protection to provide some environmental control. And you can see that the whole of that area, which goes pretty much halfway across the Pacific, with the Hawaiian Islands just coming in the north up there, is about 6.5 million square kilometres. So these are maps produced by the International Seabed Authority showing the distribution of some of these resources. So the 2 colours on there, the yellow and orangey colour, are a claim in the Indian Ocean by the Indian government. That's the only claim so far in the Indian Ocean. And a recent claim has been put in the West Pacific by the Chinese. So the Clarion-Clipperton zone, where all the colours were, plus these other 2 areas are the currently licensed, currently contracted areas by the International Seabed Authority. So areas with manganese nodules are very peculiar environments. They're in the more remote parts of the oceans, and so very little research has gone on in these areas. But what we are beginning to find out is they've got very high species diversity. So it's quite common when you take a new sample of the seabed, you find many new species, and quite often more new species than known species in every single sample. The individual organisms are quite widely distributed. There's a particularly low biomass here, so in any one sample there may be a very small number of individuals, particularly large individuals. But many of them may be long-lived, and they live in this environment which over at least part of the Clarion-Clipperton zone has very stable conditions. And we know, as I'll come back to later, that these animals find it very difficult to recover from disturbance. So, on the engineering side, there's been quite a lot of development going on for manganese nodules. This is a vehicle developed by the Koreans, and it would shoot water jets onto the seabed just in front of the vehicle, which would then loosen the nodules from the sediment and then scoop those up with a blade which goes into the sediment, and then wash them as they go back, and then extract the nodules from the fluids and take those up the riser pipe in a slurry, and then dump the rest of that sediment-laden water behind the vehicle. The Indians have been developing a vehicle for their claim in the Indian Ocean. This is Royal IHC in the Netherlands. They're in charge of the other project that I'm working in, which is called Blue Nodules. Dini, one of the big dredging companies in Belgium, they've developed their own vehicle and recently attempted to test it in the Clarion-Clipperton zone, but unfortunately it failed, and they're going to have to wait another year before they can do that. This is an old picture of a mining vehicle from what is now UK Seabed Resources, and they were one of the first to do mining way back in the 80s, with this vehicle, which has a peculiar screw motion as you can see, the long yellow bar on there which drives it across the seabed. China has a lot of claims for manganese nodules, and they are building their own vehicle. Interocean Metal is a consortium of companies in Europe and Russia, and Cordy, the one I showed before. So all these vehicles are now under development. I'm not sure any of them are completed, or there's a full-scale model of any of them, but certainly all under development. One of the big problems with mining manganese nodules is the plume, and it's graphically shown here. So the area that has to be mined, as I explained earlier, is very large, but the plume could extend the area of impact quite considerably beyond the mined area. So there are two aspects of the plume. You can see the vehicle on the left there, and it's pouring out this slurry, which will run straight across the seabed, and then part of the plume is going up into the water column. And because it's made of very fine particles, it can travel a long way. The sediments which the nodules are found in the Clarion-Clipperton zone is pretty much clay-sized, so once it's in suspension, it's very difficult to get it out of suspension again. And it could go long distances. So this is a model which was done in the IMarEST project, which was a European-funded project, and we had a lot of scientists and engineers and NGOs and policymakers in the project. And Andy Dale from SAMS in Scotland built a theoretical model of what would happen with a mining vehicle and where the plume would go. It doesn't properly show the plume which goes into the water column and spreads huge distances, but it shows what would be deposited from that plume on the seabed. So if I run it should run. Yeah, and it's over 1 year using, as far as we knew at the time, real conditions. And the yellow box, the green box, which is the mining box area, is 12 kilometres by 12 kilometres. So you can see it's not a simple ellipse around the mine site. It goes off in different directions according to the currents, and the currents used in the model were a genuine set of currents for that area for 1 year. So when you look at it in detail, it looks like this, and you can see areas where 0.1 millimetre is deposited, or 1 millimetre or 1 centimetre, which sound like very small amount of additional material to the seabed. But this area probably receives 0.1 millimetre in hundreds of years. It's orders of magnitude more than these organisms are used to. And we expect that they will be disrupted or killed by a reasonable amount of this deposit. And we're not quite sure how far out these plumes will have this effect on them. So if we take a square box of 75,000 square kilometres, and which would represent a mining claim, the contractor eventually will choose mine sites within that, and they may eventually mine 20% of the total area or 30% of the total area in maybe 2 or 3 different boxes. So the dark blue is then the mined area where everything has been taken up the pipe and would need them to recover for some hundreds or maybe even thousands of years for everything to come back properly. But here you can see also the area that could be affected by the plume. And this may spread for tens of kilometres or in some model even more than that beyond the mine site. So we put on here an example of 50 kilometre plume. And if you had 3 areas that were eventually mined, the whole of that 75,000 square kilometres could have some form of impact from these, either the mining itself or the plumes. So one of the big engineering challenges is to reduce that plume down to the minimum. I mean, there's always going to be a plume, but could it be reduced to the minimum by good engineering design or by some technique such as flocculation or some other method? I really think that this is something that good engineering design might be able to work on. And in one of the other projects that we're working on, we're trying to think about how you might define the point at which the impact is negligible. So obviously next to the vehicle, the impact is going to be very strong, and it's going to go some tens of kilometres. This is not a real scale on here because we don't know how far it's going to go. And it's going to have an impact on the fauna. and it's going to destroy some of that fauna, and at some point it's going to have a negligible impact, but the plume will probably carry on going and depositing very small amounts of material. So what we really need to define is the effective age of that plume, and we don't really know how to do that. So it may not be where I've put the arrow, it may be a lot nearer to the mine site, for example. And then we might be able to measure the different capacity of each vehicle, the different potential for each vehicle, and by following best available technology, hopefully that would then be incorporated. The better vehicle would be, the designs would be incorporated into all the other vehicles. Here you can see the problem. So this, it was actually a dredge line. You can see it going up the left-hand side of the picture there, diagonally. This was a dredge trawled across here more than 26 years ago. And it looks as if it happened yesterday when you go down there with ROVs. Nothing is really recovered, nothing is turning the sediment over, nothing has come back to life. Well, the small amounts of animals have come back to life in these areas, but certainly not the full fauna that we had there before. So what are the reasons for this? So here you can see a representation of a cross-section of the sediment, so the sediment surface at the top, where animals living on the sediment or in the sediment, or many of them actually attached to the nodules itself, which is what the right-hand little spiky thing shows on the top there. Mining will probably take off 10 centimetres or so from that, and that includes just about all of the biological active layer, which is probably in the upper just a few centimetres, so all the biology lives in the very top surface. Because these sediments accumulate incredibly slowly, probably less than a millimetre per 1,000 years, and there's a very, very slow rain down of material, so there's nothing there to eat below a few centimetres, and so all the biological material is in the top. This will then be planed off by the mining vehicle and dumped back behind as the slurry that I talked about. But it won't have the same composition as what was there before, because that previous material had most of its water removed by progressive compaction over many thousands of years. The new material will be highly water charged and very difficult for animals to burrow into or to attach onto. And so the biological material, all that surface bioactive layer, will also be lost in the mining process. So, how long will it take for that material to consolidate down again so that the organisms can start inhabiting it? And how long will it take for that rain down of new organic material to build up enough so that the organisms can actually get established again? And we really don't know, but we know, having looked back 40 or 50 years at examples of where things were disturbed, that things have not come back fully at this time. And then, of course, the nodules themselves, shown here again on the right, they take millions of years to grow, and so they're never going to come back, the nodule fauna. And quite a lot of fauna does live attached to the nodules. So, here we go back to that example of the map again with 3 potential mineable areas. The plume is probably likely to do something more like this rather than a square box around the mine site. But we also have this slurry layer, which is coming out the bottom. And the two may go in different directions. So the slurry layer, we've only just started thinking about this. We just assumed everything was a plume before, and then we suddenly realised we might have this layer. So this slurry layer will go down slope. And we know in the Atlantic, in the Madeira Abyssal Plain, which is fed from the African margin, we get turbidity currents. And these are where pieces of continental margin break away and slide down into the deep ocean. The last one occurred exactly 1,000 years ago, and if you take a box core in that material, bring it on deck, turn it sideways, it will flow out. So it still hasn't consolidated after 1,000 years. We don't know whether these sediments will behave the same or differently, but if they take a long time to consolidate, it will mean that it will be a long time before these organisms can properly recolonize. And again, maybe there's an engineering solution that can help the dewatering of this slurry, or prevent so much being formed in the first place. So what I mentioned was that they're going to plane off the seabed here, And so originally it might look something like this, with sediment layers, nodules sitting on the top, because they all sit on the top of the sediment. And then the mining could flatten that completely and then dump a slurry layer on top. But that's probably not good for the fauna because everything's homogenized and you've got this slurry. So if you were able to put some sort of small plough behind the vehicle, maybe you could make a ridge and furrow type topography beyond the mining. And then the slurry layers may go into the troughs and the ridges may stand up as harder substrate. So we're not sure how quickly each is going to recolonize, but there's two choices at least in the system there. And then if you have something like that, and one of the possibilities is to enhance the recovery, particularly of the organisms that live on nodules, by putting synthetic nodules back into the area to make attachment zones. So these would have to be very carefully manufactured. And often the sponges grow on the nodules and they have a long sponge stalk. The sponge dies, but the stalk stays there. And then other animals attach to the sponge stalk, and you get this complex community. Well, you could probably attach something to these as well. And so you could drop some nodules from the ship, and maybe some of them then would land on the ridges where they wouldn't sink into the bottom of the slurry and be lost. So it may be a simple engineering solution that has a big environmental benefit. So the deep sea plume is bad enough, but there are also two potential other plumes. So when the material, the slurry, goes up the pipe to the ship, it has to have the water taken out of it because the ores have to be transported dry. And that water is returned to the ocean. At the moment, the criteria is that it should be deposited below the thermocline, roughly 800 to 1,000 meters. But there, if it's got lots of particles in it, and it's in a very particle-pure, poor part of the ocean, then that might have an effect on midwater organisms by clogging their filter feeding or preventing proper ecosystem community activities. Then there's a third one, which is the ores will be stored on the ship in a dry state, and maybe once every week, 10 days or so, a barge will arrive and offload all that material and then take it away. One of the options that was being looked at was the transshipment of that in a wet state. So the ores were going to be re-wetted, transferred to the barge, then dewatered, and that water was going to be put back into the ocean. So you end up with 3 plumes in total. So what we have been suggesting recently is that you take the transshipment plume, add it to the returned water plume, and put all of that back near the seabed, and then you've only got 1 plume and 1 impact on the ecosystem down there. It adds another engineering challenge, but I think it should be feasible. I think we have multi-flow pipes in the oil industry. So let's move on to polymetallic sulfides. Here you can see some of the organisms that live here. These are deep sea mussels, and the areas that are to be mined are exactly along the mid-ocean ridges. As you can see here, you can see that they follow exactly that boundary. This is in the North Atlantic. There are 3 contract blocks. There's the blocks of the Polish government, and then the French government in green in the middle, and then the Russian authorities in the bottom. I showed this map before when you were looking at the yellow and orange, but now if you can see them, there's a thin trail of blocks which run down to the east of Madagascar and then down just south of Madagascar. 3 more mining claims in there. So these are formed on mid-ocean ridges. So here you can see a mid-ocean ridge. This is where the lithospheric plates of the ocean move apart and new crust is generated by magma activity along the center. And that heat and volcanic activity can draw water into the crust, take it through the crust where it's heated, where it will dissolve metals, and then it comes out at the seafloor in particular areas along the ridges called hydrothermal vents. They're not continuous along the ridge, they occur in sporadic occurrences. I think there are about 18 in the North Atlantic, so not very widely distributed. But these are active for a certain amount of time, and as the plates get older, they turn off, new ones pop up. And and then they become inactive vents, and they may maintain some metals, because the metals are precipitated when the water comes out at the seabed. So this is what the mid-ocean water looks like in detail. This is from the South Atlantic. You can see the white line shows the ridge axis. You tend to have a deep valley where the main activity is, and then up on the flanks you can still get volcanic activity and hydrothermal venting, and then the rocks just become too old as they move away from the axis. That's a black smoker or a typical hydrothermal vent, and they have very charismatic faunas that can live on them. So these faunas are independent of light. They use the hydrothermal fluids as a source of energy, and the whole community develops, starting with bacteria and then moving up to higher organisms. They're pretty unique, these faunas. They only cover a few square kilometers globally on these ridges. It varies on a regional basis, so it's not the same in the Pacific as the Atlantic, and not the same between the North and the South Atlantic. They can be very dense, so very high biomass, but relatively few species. And they have a chance to recover probably quite a lot quicker than in the nodule-bearing area, so we're not quite sure how long, but maybe tens of years, a few tens of years. Because these vents do come and go, so they have this method of propagation to the new vent sites. So most of the work on finding sulfide deposits is carried out by looking for those active vent sites, because they give off this large volume of fluid which goes up into the ocean. It can come out at 400 degrees centigrade, shoots up into the ocean, and then levels off. It's reduced its temperature back down to ambient by about 200 to 300 meters above the seabed, and then it forms a layer which can spread out naturally. So you can take an AUV or an ROV or other instruments and put it down. You can seek out those hydrothermal plumes, map them, follow their gradient back, and find the black smoker at the end. And then either measure the metals in that individual sulfide, or you can look for inactive vents which often cluster around the active one a few kilometers or so of distance, and that would be called a vent field. As those vents get older with time and they start moving away from the ridge axis, then sediment begins to deposit from the surface ocean on this new crust, and it gradually builds up layers that eventually become the hundreds of kilometer thicknesses that we get on the ocean margins. But you can't easily find sulfides buried under those sediments. And the Japanese have just, and some others have just been working on equipment to try to do that. And don't ask me to explain this because I don't fully understand it, but this is self-potential measurements that can be carried out where you tow this vehicle at a set depth above the seabed. You have an inclined array behind that, and you can measure the self-potential. And this theoretically can look a few meters or even a couple of tens of meters into the seabed through the sediment and find a buried sulfide body underneath. I think these instruments will be developed more into that in the future. So in terms of practical mining, these are instruments that were built for Nautilus Minerals, a Canadian company which has recently been in receivership, and this was all aimed at mining a fairly small area of Papua New Guinea, with about nearly 2 million tons of ore. So you see on here the auxiliary cutter at the top. This would be used to flatten the seabed, and then you get the block cutter bottom left, which would strip mine the flat areas, and then that would have to be replaced by the collector, which would then be lowered down and hoover up the ore. So 3 separate vehicles to do the mining. The Japanese, in 2017, actually did some test mining. They actually mined sulfides of the Okinawa rock. This is the vehicle that they designed and used. It's very much a prototype. And the mining activity looked like this. So again, flattening off benches, mining those benches, taking the material and passing it up a riser pipe to a waiting barge. So very recently, some brochures have come out from a company called Bauer in Germany with a slightly different design. So the previous methods would have caused a plume even for sulfides. It would be different material because basically they're grinding hard rock here and chipping that up. But it still would generate some rock flour which would go into suspension. But the Bauer instrument on the left-hand side here is essentially a trenching tool, a multi-trenching tool in one instrument, which can be used, just lower it to the seabed. It can drill in about 7 meters, I think, and then lift it up, drill adjacent to it and adjacent to it. And here the plume can be collected pretty much in its entirety, apparently, and taken up the pipe and taken up to the ship to be dealt with. So this, I'm not sure, this is meant to be a copy of an on-land machine, just modified for deep sea. Maybe quite effective. I've been working on this project trying to develop a regional environmental management plan for the Atlantic Ocean, specifically for sulfide deposits, working with the International Seabed Authority. So these next 3 slides just show a plan view of part of the Atlantic Ocean. So down in the middle there you can see a thick black line which is meant to represent the axis, the spreading axis where these plates move apart. And then you can see on it some very small red dots which are labelled active vents, and these are where these hydrothermal material is coming out at the seabed. And then along this rocky substrate, which forms a fairly narrow band down the mid-Atlantic ridge, we get attached colonies of corals and sponges in some areas. So the blue area represents the dashed lines on here now represent about the maximum that we know active venting occurs away from the ridge axis, about 12 kilometres, maybe occasionally a little bit more than that. And most of the contractors are looking up to about 20 to 30 kilometres away from the ridge axis, and when I talk to them in detail, they say they probably won't even think about looking for mines beyond about 50 kilometres. So all the mining will be concentrated in that very narrow band down the mid-Atlantic ridge. So this is what a mine could look like. The bright small green dot is meant to represent the mine, which could only be in the order of 1 square kilometre or so very small, but it could generate this plume. So we don't know how far that plume is going to spread. So on here I think I've taken a 5 kilometre radius and I've turned it into an ellipse because the flow will go with the topography, which is these longitudinal ridges, and it will also be taken by currents, which also go in the direction of longitudinal ridges. But we don't know how far it will spread. But if that plume wasn't managed properly, and was a much larger plume, and there were 3 mine sites in relative proximity, then you could be having impacts across the whole of the ridge, and that probably represents cumulative impact. So really cutting the plume down to the minimum has a big environmental improvement, and it also could potentially lead to more mining. And if that plume could be really managed down by using something like one of these new instruments, then you'd have a very small footprint, and depending on the total number of mines, the impact of deep sea mining for polymetallic sulfides, as long as it was in the right areas and probably not on those active vent sites, might have a relatively small footprint. So all of this is quite important because this is an actual published account of some locations of ores. So the Russians have published this and predicted that there could be 40 million tons of ore here. So if they're mining 2 million tons a year, this could be a mine in place for about 20 years on one small site of the Atlantic. Unfortunately, one of these sites has got an active vent community, and there's a big push not to mine active vent communities. It's site number 2 on there. But if you were mining the closest adjacent site, which is 5, and you only had a 2 kilometre radius plume, then it probably wouldn't reach that site. But if you had a 4 kilometre radius plume, it might overwhelm that site. And we still don't know what effect the plume will have on these vent communities, because they do live in a very harsh, toxic, potentially particle-laden environment anyway. But you can see that real control of the plume enables you to have a much smaller environmental footprint. So the third type of mining, and this one will be quicker because we know much less about cobalt crust mining. But even so, there are some contracts already approved for exploration, mainly in the Northwest Pacific. They're very small to see, but they're on tops of seamounts. And so the contractor will have chosen a whole variety of seamounts to explore, and then we'll have to choose one or two sites eventually to put forward for mining. That's an image of what a cobalt crust looks like. So you see this thick black deposit attached to the top of the rock here. And what are the environmental credentials of the organisms? Well, here again we have, on tops of seamounts, you often have diverse ecosystems with many species. They're often not very well studied because they're usually in the middle of the ocean, which is difficult and expensive for scientists to get to. But they tend to be fairly stable ecosystems, often slow-growing organisms, and some of these can live for hundreds and several hundred years occasionally. And so recovery of these will probably be very slow and quite difficult after mining. And we don't know whether those organisms specifically like the crust or whether they're happy with any hard substrate. And it's also the large scale of mining which could have quite a wide impact. So I showed you some bits about technology for the others, but really we don't know much about technology for cobalt crusts. There are two main issues here. So firstly, to find the total extent of mineable crust. So the contractor will need to know the area and the thickness, and if the thickness varies over a reasonable size area, then it will have to be measured in quite a detailed fashion. And I don't think instruments have yet been developed, geophysical instruments, that can be deep-towed over these seamounts to measure the thickness of crust as opposed to the underlying rock. It's got to be quite a sensitive difference between the two. So that would be the reconnaissance to work out the total amount of ore. And then secondly, because the crust itself is probably on an irregular surface and the rocks underneath are probably irregular, if you bring up much of the underlying rock as well as the crust, then your total amount of metal goes down in the total material mined. So you should only be mining the crust and not the underlying rock. So probably it would have to be something like this, with many multiple mining heads, each of which is capable of sensing the thickness of the crust and going up and down as the vehicle moves forward. So another fairly large engineering challenge, and I'm not sure these have been tackled yet. So just to finish off, a couple of common issues between all the mining types. One is the riser plate, which I haven't talked much about, but going from whatever it is in the oil industry, 3,500 meters or so, into the deep of 4,000 to 5,000 meters for nodule mining might be quite a challenge itself. And this material, of course, is not hydrocarbon, it's pieces of rock which are going to be forced up the pipe. So just adapting oil industry riser pipes to this industry and then going a lot deeper might be a challenge. But coming back to this Bauer slide again, in the middle image, just above the seabed there, you can see, well, it's rather difficult to see, but there's a sort of cage there, and the cage is actually enclosing a sort of tank which can be loaded with ore and then taken up to the ship, dumped, dropped back down again. So in this case, you wouldn't need all the water in the ore because it wouldn't be using water to pump it up the riser pipe. It could be pumped up with a very small amount of water, which significantly reduces the requirement to dewater on the ship, and it reduces the environmental impact of putting that water back down somewhere. And engineeringly, it may be an awful lot easier than trying to develop a riser pipe. So that's being thought about. Then there's all the aspects of the ship, and I'm not going to go into any of those here, but certainly it would have to have a pretty substantial dewatering plant. It would have to be able to store quite a lot of ore, waiting for the barges to come. It would have to have a lot of power generation to hold position exactly and to drive the vehicles on the seabed, and it would have to be very precisely controlled so it didn't cause that mining vehicle to lift off the seabed as it's going along, and so that it could also transfer ship to ship its material once every few weeks or so. So in conclusion, after several years of relatively low activity, deep sea mining is now firmly on the horizon. People are taking out contracts to explore for different areas, and they're building equipment. The ISA is now actively developing its mining code to set in place all the regulations so that mining companies can then try to borrow the money they're going to require to do all of this expensive work, and to build all this complicated technology. And there's still a whole series of challenges here. I mean, there's lots of other engineering challenges, I'm sure, but I've tried to pick out those related to the environment, that where we could make, if we made progress, then we can have a much lower impact on the environment. And finally, I'd just like to thank the 3 projects that I've been involved in, which is Blue Nodules, where we're trying to develop a collector vehicle for nodules with as minimum environmental footprint as possible, and Blue Harvesting, which is trying to take that a little bit nearer to market, and then the Atlantic Rim project, which is trying to work out an environmental management plan for the Atlantic Ocean. So I'll finish there. Thank you.
Phil, that was absolutely fascinating. Thank you so much for that. We've got some time for some questions now. Questions from the audience here, and also questions from any of the audience who are on our live stream. Kaz, I don't know if we've got anything yet on the live stream, but if you just wave at me, I'll go to you. But I can see one straight away from Barry in front here. Could you please wait till we have the microphone, because otherwise the people on the live stream won't be able to hear the question.
Fascinating lecture. I've been waiting for years to find out what's been going on and not going on. I don't see them. I'm a fellow of the IMarEST and a trustee, and I used to operate underwater in nuclear submarines for the Royal Navy, not as deep as you're describing. We're very conscious in recent weeks of extinction rebellion and all about climate change, and the world's not doing enough to protect the environment. How would you convince people that this is a sustainable, right thing to do?
Well, I'm not a contractor, so it's not my job to say the benefits of all of this. I can give you the arguments which they give. So particularly for nodule mining and crust mining, there are elements which are used in modern day batteries and a lot of modern technology. That's not so much the case for sulfide mining, which is really about copper and gold, essentially. But to be honest, both nodule mining and crust mining do have this big aerial impact, both through the mine itself and the potential of plumes. And we're a long way down the road to licensing or to approving mining activity in those 2 types of substrate. So if we're going to go mining, my real drive is to reduce the other effects, the secondary effects of this plume as much as we can, and try to get in now before people actually finish the designs for their equipment and it becomes too late to change the direction. So we're trying to identify all the issues, get them on the table, and if people can think and say, oh, that's a good idea, this new barrel instrument that could contain most of the plume, then that needs to be promoted quite quickly to the other contractors. So I'm not sure we can do everything, but we're trying to do what we can.
I think we had a question down here at the front. Just back there, thank you.
Thanks very much. My name is Helen Paul. I work with the Conventional Biological Diversity, where there has been some discussion of this, but far too little in my opinion. And I'm wondering how we really get a proper discussion with a wide range of people about the environmental impacts, because I feel as though there hasn't been nearly enough yet of that kind of discussion.
Yeah, the BBC have taken quite an interest in deep sea mining from a UK perspective. I know that's not global. And there is a very good article by David Shipman on the BBC website that goes into this. And recently he was out on board with the Blue Nodules cruise, and he gave a short little description of what was going on there. Other people have had meetings in various places, and it's come up, but there's an awful lot going on in the world, and juggling all of these things, I don't know how you get much wider debate. But big debates go on in the International Seabed Authority twice a year now, in February and July, where most of the states of the world turn up and discuss environmental impacts, the regulations, and a whole series of other aspects of mining. And probably if you have more of your concerns would have more weight if you dealt with your respective governments, who then take everything forward to the Seabed Authority's annual sessions. That's probably the best way.
The question is very back corner.
Phil, Nick Lambert, Chartered Fellow of IMarEST, fascinating presentation. Thank you very much indeed. Wet question time now. Could you just talk about the techniques that are being used to develop these processes? Because it looks a bit like open cast mining. Are the contractors thinking really laterally about how they will go about recovering these materials from the seabed? That's the first question. And the second one is, how does the environmental impact caused on the seabed compare with the environmental impact of open cast mining in somewhere terrestrial? Are they similar, greater, lesser? Thank you.
Good questions. The contractors, of course, don't put out all their information, so we don't know exactly what's going to happen, but there are bits of information. The bow pictures, it's mentioned in a paper, was a lot of the maths behind the development of the kit, and then in a brochure, and that's about all I've got to go on. So I don't really know what's going on behind the scenes, and I don't know whether different instruments are already much better than other instruments. What we don't want to happen is just copy some cheap and dirty method and everyone take that as the norm, and then not put much effort into engineering design. I have talked to some engineers who say no problem is insurmountable if we have enough money. But I don't know how much money you need to get over some of these plume problems. Sorry, your second question was? Oh, the relative impact, yeah. The relative impact, the difficulty with the sea is that you are putting things into suspension which you then can't control. So if you have an on-land mine and you make a lot of dust, you can wet it and then it settles. You can't do that in the sea, so you've got to have some other methods of that, and I don't know what those are. I don't think anyone does. One possibility is flocculation. If you mention that in a room full of biologists, they all throw their hands up in horror saying you mustn't be putting chemicals into the ocean. But if you're putting toxic plumes or particle-laden plumes in the ocean, which are going to have a very negative impact, and you could flocculate to reduce the size of the footprint of that impact, then maybe that's something that should be thought about. Beyond that, I don't know. And so you end up with the hole in the ground from on-land mining, but you don't end up with the plume impact, and also the hole in the ground is probably quite a lot smaller for nodules and crusts, but not for sulfides.
Okay, we have a question from one of our live stream participants.
So a couple of questions from those online. Firstly, depending on the current R&D level, when is full-scale commercialised mining expected to commence? And secondly, has there been any research into the toxicity of raw material or endemic species found around the nodules?
Yeah, when is mining likely? So the contractors can't really line up all their investment until they know all the regulations. So the regulations are not yet in place. The International Seabed Authority is working on producing a draft of those regulations for the July meeting this year, or February and July, I think, and they're hoping that they might be in place by July this year. But I think there's a whole lot of other legislation that needs to go with those core standards and guidelines, and I'm not sure how long they're going to take to develop it. I think some people are hoping that it's all going to be done by 2020, and other people think it might take a little bit longer than that. But probably until those are in place, it would be difficult for companies to get all their money, and then they've got to have some time to line up the money, and they've got to do all the technology development, and they've got to do the testing. So we may be, I don't know, 7 or 8 years away from mining. If you read the Bauer brochure that I mentioned earlier, it says 2027, 2028, something like that. And the Japanese, I think, have said, although they've done test mining now, they've said it would, for themselves it will be 10 to 20 years before they're ready to actually mine, even though they've proved that it's feasible. And then the other one was a biological question about sensitive habitats. I've been in a meeting all last week in Portugal talking about these very sensitive habitats and trying to identify what they might be, and using other criteria such as FAO VNE criteria or something like that for the International Seabed Authority, where we could then say these sites are important to preserve and shouldn't be mined or should be mined in a very limited way. For nodules, there's many biologists trying to rapidly understand the biological communities for manganese nodules, and it's now starting to come together as a picture, but very difficult because huge areas and many, many unknown species.
Time for one or two more. There's a return questionee at the front here.
A couple of things you've said trigger further thinking. You referred to licensing and then rapidly withdrew the term.
It's easy to say the word license. It's more difficult to say the contracts. So they are contract. They're all contracts given out by the IMarEST.
But I'm just wondering who is going to police this activity? It's difficult enough on the continental shelf, but this is literally out of sight completely.
Yeah.
The ISA might set the rules and regulations, but who's actually going to police it?
So the ISA have the ability to set up a regulatory authority, which would be part of, come under the auspices of the ISA, but so far they haven't done that. And they say they can't do that because they don't have enough money, and they won't have enough money until they go mining, but by the time they go mining, the regulator will be a bit far behind the curve. So that's how it's meant to happen. And it's quite important that the two are separated, so that the arm of the ISO, which is working with the contractors and negotiating new contracts, should be a little bit independent of the arm which is regulating, otherwise you end up in the mess that we had in the Gulf of Mexico.
But then you need a police force.
Well, yeah, so monitoring is another major issue, and as I've said, these areas are very remote from land, and therefore fully independent monitoring may be very difficult or very expensive. So it may be the contractor has to monitor their own activities, and we're getting better with sophisticated tools which can track vehicles, track ships, verify information, but I'm not sure how all that's going to come together at the moment.
Okay, thank you very much, everybody, for your questions and contributions. Phil, I want to say a very big thank you to you for coming on this evening. It's very difficult to think of a challenge that better embodies marine engineering, science and technology as this one, and I think it's challenge with a capital C, which is going to keep the community very busy and active probably for many decades to come. So I'm very grateful to you, Phil, for your time this evening, and I'd like to give you this small token of our appreciation for the lecture this evening. Thank you very much.